In other videos, we have talked about the idea that even for a given element, you might have different versions of that element, and we call those different versions isotopes. And each isotope of an element can have a different atomic mass. And that stems from the idea that if it's a given element, it's going to have the same number of protons, but you could have a different number of neutrons. Now, one question that you might have been asking yourself is, how have chemists been able to figure out what the various isotopes of an element are and their relative abundance? What percentage of an element that we find in the universe is of isotope A versus, say, isotope B? And the answer to your question is they use a technique known as mass spectrometry. I can never say it right. Mass spectrometry. Sometimes you'll hear the word mass spectroscopy, and they're essentially referring to the same idea. And what this technique is that you put a little bit of a sample right over here. Let's say we're talking about zirconium in this example, and you heat it up. So you have a bunch of the zirconium floating around, and then you beam it, you bombard it with a bunch of electrons. And what the electron bombardment does is it can knock off electrons from the atoms in your sample, and it can ionize them. And by ionizing some of your atoms, they now have charge. And because they have charge, they can be accelerated through these electric plates. So now you have these ions, in this case of zirconium, moving quite rapidly through this chamber. And then they enter into a magnetic field. And a magnetic field, a strong magnetic field, can bend the path, can deflect ions with charge. For a given charge, the force of the deflection will be the same, but if you have a larger mass, you're going to be deflected less. And if you have a lower mass, you're going to be deflected more. And so what you see here are the different isotopes being deflected different amounts as they go through the magnetic field. And then you have the detector, and at different points of the detector, you will detect each of these isotopes. And the more ions that hit a certain part of the detector, that means that, hey, I have more of that type of isotope in nature. And then from that, you can generate a chart that looks like this, where you see on the horizontal axis, sometimes you'll see it labeled atomic mass, and here it's in unified atomic mass units. And you can see when you put the zirconium through the mass spectrometer like this, you get a little bit that has a mass number of 96. You have a little bit more that gets a mass number of 94, 92, 91. And most of the zirconium, over 50%, has a mass number of 90. Now, in other cases, you won't see it just in terms of atomic mass, given in unified atomic mass units. Sometimes in this horizontal axis, they'll give it in terms of mass to charge ratio, where mass is the mass, but then charge is essentially the charge of the ions. Now, in a case where your charge is 1, for example, if you knock one electron off of the atoms and you have a +1 charge, well, then the mass to charge ratio would be the same thing as atomic mass, measured in unified atomic mass units. If your ions have a different charge, well, then you would have to make the appropriate adjustment. But in an introductory chemistry class, most of the time you will get things in terms of just straight up atomic mass. If you happen to get something in terms of mass to charge, just make sure that if the charge is, say, +2, that you make the appropriate adjustment for the masses. But this right over here will tell you the various isotopes, and it will tell you its abundance. And it all comes from this process of ionizing those atoms, speeding them up, deflecting them through a magnetic field, and the ions that have a higher mass to charge ratio will be deflected less, and the ions that have a lower mass to charge ratio will be deflected more, and you can use that information to make a graph like this.